So first we need a few definitions to start us off. Independent events are ones that do not affect the probability of each other. So, for instance, independent events might be, it was cloudy this morning and the cafeteria ran out of muffins for breakfast. Okay, did they run out of muffins because it was cloudy? No. Is it cloudy because they're out of muffins? No. Those things are not related. They are completely independent. Now something that would not be independent. Let's say it's cloudy today, so I brought an umbrella to school. Are those things independent? No, because there is a relationship. Am I more likely to bring an umbrella if it's cloudy outside? Yes. So knowing that it's cloudy changes the probability that I bring an umbrella. So those are not independent events. So independent just means they have nothing to do with each other. Dependent, there is some kind of relationship. It doesn't necessarily mean one causes the other, but it's saying knowing one thing happens will change the probability of the second. Dependent. So suppose you draw a deck or a card from a standard deck of 52 cards and then roll a die. So the event drawing a heart and rolling an even number, are those independent or dependent? Independent. Does the card I draw out of the deck change what number my dice is going to land on? No. B. Suppose two 40-year-old women who live in the United States are randomly selected. The events woman 1 survives the year and woman 2 survives the year. I just take two random people in the United States. One of them surviving the year, does that change the probability that the other one lives all year? No, they're two random people. Now, if I took like two people in the same nursing home, could those be related? Yes. You know, if we're thinking about illness or something, but if I'm just taking two random people in the United States, those would be completely independent of each other. C. Suppose two 40-year-old women live in the same apartment complex. The events woman 1 survives the year and woman 2 survives the year. That would be dependent. Okay. Not that, you know, one of them not surviving means the other one wouldn't, but if you think about, you know, let's say they live on the coast and there is a hurricane. You know, if that hurricane hits the apartment complex, that would change the probabilities of those two women surviving. They're in the same place, same location, so there is some kind of relationship there. So far, so good? If events are independent, then to find the and probability, all we have to do is multiply their individual probabilities. So or is when we add, and means multiply. And this can be extended for more than two events. So if I had three unrelated things and I want to know the probability of all three happening, you just multiply their probabilities. So this is the multiplication rule for independent events. This is on the formula sheet, and that will be the piece we are looking at today. So let's do an example. So the probability a randomly selected female age 60 years old will survive the year is 99.186%. What is the probability that two randomly selected 60-year-old females will survive the year? So are those independent? Yes, these are independent. So all we have to do, probability they both survive, or let's let's just write it as survive and survive. So and means multiply, so you just take your individual probabilities. So 0.99186 for the first and for the second. And that 0.9838. So there's a 98.38% chance that they both will survive the year. Alright, so B, the probability that 4 of them survive the year. What would we have to do? Multiply it 4 times. A shorter way of doing that, you could just write it to the 4th power. Either way. And we get 0.9678. Any questions about those? Let's look at this problem. So the probability that a randomly selected female age 60 will survive the year is still the 99.186%. What's the probability that at least one of 500 randomly selected 60-year-old females will die during the course of the year? Okay, so there is a lot more to this, right? I'm asking the probability that at least one person does not survive. So first of all, is there a difference between, if I numbered my people 1 through 500, is there a difference between the first person dying and the 7th person dying? Is that different? Is it? I mean, is there a difference between me dying and Joshua dying? Yeah. So would we have to consider all of those probabilities? Yes. So you have to first consider each one of the 500 people could be the person that doesn't survive, or there could be 2 that don't survive, or 3 that don't, or 4 that don't, all the way up to 500, because I just asked for at least one. So how on earth can we go about computing this probability if we don't want to sit here all day?
Could you do like the complement?
Yes. At least one person dying is the opposite of everybody surviving, right? So we could do this as a complement, like we talked about yesterday. We have this complement formula. That's just 1 minus the probability of E. So the probability of at least one dying is 1 minus the probability that they all survive. How would I find the probability that they all survived?
1 minus 0.9916.
But this is just for one person, and I have to find out how much probability that 500 people survive, so it needs the 500th power. So there is a 98.32% chance that somebody does not survive the year. Yes, ma'am.
How did you do the problem?
You use the little caret for your icon. Other questions? Let's look at another one. A manufacturer of exercise equipment knows that 10% of their products are defective. They also know that only 30% of their customers will actually use the equipment in the first year after it is purchased. if there is a 1-year warranty on the equipment, what proportion of the customers will actually make a valid warranty claim? Okay, so what they're saying, they know that 10% of their products are bad. But if somebody's going to figure out their exercise equipment is faulty, they have to be using it in the first place, right? If they're not using it, are they going to realize there's something wrong with it? No. So they're trying to figure out how many people are going to make a warranty claim. To make a warranty claim, we really just need it to be, we need to know the probability that it is defective. And not only does it have to be bad, but they have to be using it so they figure out it's bad. All right. What is the probability that it is defective?
10%.
So 0.1. And means multiply. What is the probability that they use it? So if we multiply those, we get 0.0. So they're only expecting to actually repair 3% of the equipment they send out. Questions? That is actually the only piece in this section. I don't want to start the next section. I want to give you guys a little bit, because I know some of you were out yesterday for testing. So I'm trying to give you a little more time in class today to catch up if you've fallen behind a little bit. So instead of starting the next section, we are stopping. So you have time to get this homework done. If you are behind, this is time to ask questions.